Hello and welcome to QuantPy. In this video, we are going to derive the Ito's lemma, which is the stochastic equivalent of the chain rule of calculus. This formula applies when the Ito's interpretation of stochastic integration is assumed. Recall from calculus that, if y is a function of u, then the differential of y is defined as follows. Now, if a stochastic process, x, is a function of Brownian motion, then its differential is defined as follows. For the purists, we have implicitly assumed that the function is twice continuously differentiable, and this assumption will become explicit when we get to the proof. Comparing the deterministic and the stochastic chain rules, we see that the stochastic version has an extra term. The stochastic chain rule is known as Ito's lemma. It is also commonly referred to as Ito's formula. We can write it in integral form, as follows. And if x happened to be a function of t as well, then we will need to add one more term to this, which is just the partial derivative with respect to t, times delta t. This result is valid for a much larger class of stochastic processes, the so-called semi-martingale. But we will prove the result using the Brownian motion as an example. This is easy to do because we already know the properties of the Brownian motion and its integrals. As you would expect, extension to semi-martingale is only a matter of exposure to this broader class of processes. To prove the formula, let's write the differential as the difference between the end and the start values of the process. As x is function of Brownian, we can write it in terms of the function values as follows. Now let's divide the interval from 0 to t into n subintervals, and let's write the overall change as the sum of the changes over the subintervals. This is just the telescoping sum formula in reverse. Now, recall this formula from calculus. Notice this is an exact formula and not the truncated Taylor series. But you can view this as truncated Taylor series, which has been made exact through the mean value theorem. Notice the first derivative is at the left end point, whereas the second derivative is somewhere in the interval and is chosen to make the formula exact. Now, in terms of the Brownian increments, this formula looks longer and complicated, but we just substituted the Brownian motion value at the left end of the interval for a and the Brownian motion value at the right end of the interval for b. We also substituted k' for c, so as to make it clear that this point belongs to the kth interval. Substituting this into the summation formula, we get. Splitting the two components, we get. Now, the first term, in the limit as n tends to infinity, is precisely the definition of Ito's integral. The second term is complicated, because the point at which the function is evaluated is not at the left end of the interval that the Ito's integration assumes. And you can see that, in order to prove the Ito's lemma, the only thing we need to show is that the second component converges to an integral that we can make sense of. And that's exactly what we are going to do now. We are going to prove the convergence of the second summation to an integral in two steps. Firstly, we momentarily assume that the function value is evaluated at the left end of the interval, then given that the square of the increments term is similar to the quadratic variation of the Brownian motion, we can speculate that it converges to this expression in the mean square sense. In the second step, we then take advantage of the assumed continuity of the second derivative of the function to show that changing the evaluation point to an arbitrary point in the interval does not affect this conclusion, because the difference between the two tends to zero in probability. And thus we conclude that the expression we are after approaches x in probability, which we know can be easily written in integral form in the limit as n becomes large. Now, let's execute the plan. Recall that the mean square convergence means that the expected value of the square of the difference between x, n, and x tends to 0 as n approaches infinity. We will drop the limit for now. Substituting for xn and x, we get. And combining the two sums and factoring the second derivative, we get. This expression looks quite complicated, because we have to evaluate the expectation of the square of the sum of the product of random variables. But there is a simple trick that simplifies it so drastically as to make it unbelievable. Let's see it in action. To lighten the notation, let's represent the term inside the summation by x. Just like x square, we can write it as a product. We can split out the terms with the matching indices to get. And as the cross terms are symmetric, for example, x1 times x2 is the same thing as x2 times x1, so we can write it as follows. Essentially, we started with the square, split it into the diagonal and non-diagonal terms, and as the lower and upper triangular terms are symmetric, we just took one triangle and multiplied it by 2 to get the equivalent of the two triangles. Now taking expectation of both sides, and noting that we can interchange the expectation and sum, we get. To simplify this, we use the Tower property of expectation, which is also known as iterated expectation or total expectation, to get. If you have not seen this property before, then this simple analogy would help. Assume we have been asked to calculate the average of the integers from 1 to 4. We just add the numbers and divide the sum by 4 to get 2.5. Now, assume that we divide the list into two lists, based on whether the integer is below 3, and calculate the averages of the two lists. If we average these averages, we again get 2.5. And the iterated expectation works the same way. Now, we can take the first expectation out of the summation to get. Let's see what this means in terms of our expression, which we reproduce here. The inner expression of the first term becomes. We just substituted the expression for x. Now, we can take the second derivative, which is known at time index k-1, out of the conditional expectation. The remaining conditional term is nothing but the conditional variance of the square of the Brownian increments. We have seen this before, and is easy to recognize by recalling that the expected value of the square of the Brownian increments is equal to the length of the interval. Adding the outer summation and expectation, the first term becomes. The inner expression of the second term involves cross product, so we write it as product of the expression values at two time indices. We wrote j before k to facilitate the next step, which is to take the terms that are known by time k-1 out of the expectation. And well, the expectation term is 0, because the expected value of the first term inside the expectation is the length of the interval, which is precisely the second term, so we get 0. Hence, the second term, that is the term involving the double summation and cross terms, becomes 0. You can see this is a huge step. As that was a long derivation, let's summarize what we have established so far. We wanted to show that xn converges to x in the mean square sense, so we wrote it as follows. By expanding the square and using iterated expectation, we showed that this expression can be written as follows. Now, we know that the variance of the square of the Brownian increments is 2 times the square of the length of the interval. As the length of each subinterval is t over n, so we can write it as follows. Now, if we let n tends to infinity, then the above expression becomes 0, meaning xn converges to x in the mean square sense. And we are done with the first step. Now, for the second step, we need to show that changing the evaluation point to an arbitrary point in the interval does not affect the conclusion we just reached. We will establish this by showing that the difference between the two tends to 0 in probability. If we replace the difference between the two evaluations of the second derivative in each interval by the maximum difference between the two across the intervals, then we get. Now, the second derivative is continuous by assumption, and the quadratic variation of the Brownian motion is finite. So if we let n tends to infinity, then the product of the two tends to 0. Let's summarize the conclusions of the two steps. Assuming that the function value is evaluated at the left end of the interval, we showed that the square of the increments term converges in the mean square sense to the following expression. In the second step, we showed that changing the evaluation point to an arbitrary point in the interval does not affect this conclusion, because the difference between the two tends to zero in probability. Combining the two steps, we conclude that the second summation, in the Ito's formula, converges in probability to the following expression, which is a well-defined integral in the limit as n becomes large. To conclude the derivation of the Ito's lemma, let's reproduce a second-order expansion. Substituting for the second summation, the limiting expression we just derived, we get. In the limit, as n tends to infinity, these take the integral forms. In the differential form, this becomes Ito's lemma. In the next video, we are going to get some practice with this formula by applying it to calculate the differential of some elementary functions, such as power, exponential, and logarithm functions. In the next, but one video, we are going to use the two-dimensional version of this formula to derive rules of differentiation for the sum, product, and quotient of two stochastic processes. We will then study some of the most popular stochastic differential equations. We hope you enjoyed the presentation, and we look forward to seeing you in the next.